Okay, let's get into this. For today's deep dive, we're not starting in a lab or a lecture hall. We're actually going to start in the deserts of Iraq.
Right after the 2003 invasion.
Exactly. And the mission was, the big one, finding Saddam Hussein.
It's such a perfect starting point because all the traditional methods of military intelligence, they just completely failed.
Right. They had these standard org charts, these hierarchies that showed who was supposed to be in charge.
The formal structure.
But when they captured these high-ranking officials, they found a lot of them were, well, they were totally out of the loop.
The hierarchy didn't mean anything on the ground.
So the investigators had to realize they weren't hunting a government.
No, they were hunting a shadow network. And that meant they had to change their entire methodology.
So instead of the org charts, what did they do?
They started collecting old family photos, social notes, intelligence reports, anything that could help them reconstruct Saddam's real social links, from before the invasion.
So not who was his general, but who was his cousin.
Who was his cousin? Who went to the same parties? Who actually trusted whom? And that shift in thinking from this orderly chart to a messy, real-world map of connections.
That's what led them to him.
Directly.
Yeah.
That simple idea that networks matter more than titles, it became foundational. And it's the perfect way to frame what we're talking about today.
Yeah, because it just drives home that behind any complex system, a society, the power grid, even our own biology, there's this intricate wiring diagram.
A wiring diagram that governs how it all works and, more importantly, how it can all fall apart.
I think it was Stephen Hawking who said something like, the next century will be the century of complexity. And to get our heads around that complexity, we have to look past the individual pieces and focus on the connections between them.
So that's our mission today. We're going to dive into network science and try to pull out the universal laws that govern all these systems that seem, on the surface, just chaotic.
Because if we can understand that structure, we can start to anticipate things like cascading failures.
Right, that domino effect, like the 2003 North American blackout, where one small problem just rippled across the entire grid.
We're looking for the operating manual for connection and for collapse.
So let's start with the basics just to set the table. We use the word network all the time, right? Social networks, neural networks. But from a scientific standpoint, what actually is a network?
It's actually incredibly simple at its core. It's just a catalog of two things. You have the components,
Okay.
which we call nodes, or sometimes vertices, and then you have the direct interactions between them.
Lines connecting the dots.
Exactly. We call those links, or edges. And that's it. That's all you need.
And what's so wild is that this simple blueprint can map onto wildly different systems.
It really can. You can use the exact same mathematical representation for routers on the internet, for proteins binding in a cell, or even actors collaborating in Hollywood movies.
The nodes are different, but the map is the same. The underlying structure can be identical. And this focus on real data is what separates modern network science from, the older, more abstract fields of graph theory.
But I imagine the first step is critical. You have to draw the right map.
Oh, absolutely. You have to define your nodes and your links correctly. That choice dictates everything. It dictates the questions you can even ask.
So give us an example.
Well, if your nodes are people and your links are, say, email exchanges at work, you get a professional communication network.
Okay.
But if you define the links as family ties, you get a kinship network.
Like the one that helped find Saddam Hussein.
Precisely. Two very different maps of the same group of people.
So once we have the map, how do we measure its shape? What are the key metrics?
There are three really fundamental ones. The first is super simple, a node's degree. That's just the number of links it has.
How many movies an actor's been in, for instance?
Perfect example.
Yeah.
Second, we look at the average degree across the whole network, the typical number of connections. And the third is shortest path.
The distance.
Right. The path with the fewest links, the fewest steps to get from any one node to any other.
And these connections, they're not just abstract. They have real, tangible value. That's why tech companies are so obsessed with growth, isn't it?
It is. The value of a network doesn't grow linearly. It's quantified by something called Metcalfe's law.
Okay, what does that say?
It says the value of a network is proportional to the square of the number of its connected users.
Wait, the square. So if you double your user base.
You quadruple the network's potential value.
Wow.
And that's the logic that fueled the whole dot-com boom. It's why investors poured money into Google and Facebook, prioritizing user growth over immediate profit.
Because every new person adds value to everyone else.
The potential for interaction just explodes. In this world, Connectivity is value.
So now we have the basics down, and this is where it gets really incredible, because across all this diversity, from cells to societies, two universal laws of architecture just keep showing up.
And the first one is the one I think everyone intuitively gets, the small world property. Right, the idea that distances in networks are just surprisingly short.
6 degrees of separation.
Exactly. And that idea was around way before we had the computers to prove it. It actually came from a 1929 short story.
No way.
Yeah, by a Hungarian writer, Frigyes Karinthy. He just sort of mused that you could connect anyone on Earth through, at most, 5 other people.
And that was just a guess, a piece of fiction.
Total speculation. Until Stanley Milgram decided to test it in 1967.
The famous Milgram experiment.
That's the one. He mailed packets across the U.S. and told people to forward them to an acquaintance who might know the target person.
And he actually found...
The median number of steps was 5.5.
Unbelievable. Karinthy basically nailed it.
Almost 4 decades earlier. And this small world property, it's not just social circles, it's the power grid, it's actor collaborations, it's universal.
Yeah. So, okay, if distances are short, your first thought might be that the network is just random. Connections are just sprinkled everywhere.
That was the classical thinking. The benchmark model, the random network model from Erdős and Rényi, it actually predicts that. It shows distances scale logarithmically, which explains the small world property perfectly.
And it also predicts that most nodes should have about the same number of connections, right?
Yeah, everything clustering neatly around the average. A nice, tidy bell curve.
So where does that tidy model fall apart? If it explains 6 degrees so well, what's wrong with it?
It's wrong on the local level. Real networks show a very high clustering coefficient.
Okay, break that down for us. The clustering coefficient.
Think of it this way. If you have 2 friends, what are the odds that those 2 people are also friends with each other?
In real life, pretty high.
Very high. But in a random network, the chances are tiny. Real networks are intensely woven together in these little local neighborhoods, tightly knit groups.
Okay, so real networks are small worlds, like the random model predicts.
Yes.
And they're highly clustered, which the random model gets totally wrong.
And that deviation points to a deep, non-random structure, which brings us to the second universal law, the scale-free property.
And this is about how the links are distributed.
Exactly. Instead of that neat bell curve around the average, we find what's called a power law degree distribution.
Which means, in plain English,
it means you have a fat-tailed distribution. You have tons and tons of nodes with just a few connections, living side by side with a tiny number of nodes that have a shocking number of links.
the hubs.
The hubs.
So this power law, this is what creates what you call the tyranny of the hubs.
It is. You look at something like the yeast protein network. The average protein might connect with 2 or 3 others.
Okay.
But then you have these monster hubs that interact with over 90.
And that's not a fluke, that's the design.
That is the architecture. We find this scale-free structure everywhere.
Hmm.
The World Wide Web, the physical internet, citation networks for scientific papers, Facebook, Twitter.
And you immediately start thinking about the economic parallels. This sounds a lot like the Pareto principle, the 80-20 rule.
It's directly connected. The 80-20 rule is basically a signature of a scale-free system. 80% of web links point to just 15% of pages.
Or 80% of citations go to a small fraction of papers.
It's the same pattern. And, it extends to those bigger conversations about wealth disparity.
The top 1% idea.
Absolutely. That phenomenon where a tiny fraction holds a huge amount of the wealth, it's a power law signature. It suggests the underlying rules of the game, whether for connections or for capital, they naturally favor this kind of extreme disparity.
Let's clarify the name, though. Why call them scale-free? What does that mean?
Well, in a normal random network, the scale is set by the average degree.
The average is meaningful. It's a good yardstick.
Exactly. But in a scale-free network, the average is useless. It tells you nothing.
Because you have nodes with just one link, and then you have Google.
You have a home router with a degree of 1 and Google with a degree of hundreds of millions. The variation is so huge, there's no meaningful internal scale. You can't just zoom in on one part and say, this is typical. The whole system is defined by those massive hubs that just blow the average away. So that leads to the next obvious question, right? How do these hubs even form?
They don't just appear out of nowhere.
No. Networks grow. They're dynamic. And the model that best explains this is the Barabási-Albert model. It has 2 simple core mechanisms.
Okay, the first is just growth.
Simple as that. New nodes are always being added. New websites, new scientists publishing papers, new people joining a social network.
And the second one is the key. preferential attachment.
This is the rich get richer effect. When a new node joins, it doesn't link up randomly. It's way more likely to connect to nodes that are already well connected.
So the popular nodes just get more popular.
The probability of getting a new link is proportional to the number of links you already have.
Which explains why older nodes have a huge leg up, a first mover advantage.
That's the classical view. If you got there early, you had more time to accumulate links. But of course, in the real world, we see newcomers dethrone the old guard all the time.
Right.
So that led to an update, adding the concept of fitness.
What's that?
It's the idea that every node also has some kind of intrinsic quality or fitness that affects how fast it gets links.
So a really good idea can catch up.
A high fitness node can overcome the first mover advantage of an older, lower fitness node.
Like Google displacing earlier search engines.
Or Facebook displacing MySpace.
Yeah.
It's this constant dance between when you show up, preferential attachment, and how good you are, fitness.
And even if networks are scale-free, they're not all wired internally the same way. There's this idea of assortativity versus disassortativity.
Right. This is about how the hubs talk to each other. In assortative networks, which you see in social systems, hubs like to link to other hubs.
Celebrities date other celebrities. Top scientists collaborate with other top scientists.
Exactly. It's partly why you get the friendship paradox.
Yeah.
On average, your friends are more popular than you are.
Okay, so what's the opposite?
Disassortative networks. These are common in tech and biology. Here, hubs tend to avoid each other.
Really?
Yeah, they link out to lots and lots of low-degree nodes. They act like central distribution points. It creates this hub-and-spoke pattern. And that difference has massive implications for how the network survives.
Which brings us to the really critical part, the consequences. This scale-free architecture creates a huge paradox when it comes to robustness.
A huge one. It makes the system incredibly resilient to one kind of failure.
And incredibly fragile to another.
Yes. So let's take the robust side first. If you have random failures, just nodes blinking out randomly like equipment faults, the network is almost impossible to break.
Why is it so tough?
Because a random failure is most likely to hit one of the vast number of low-degree nodes. And taking out a tiny node, well, it barely makes a dent. It doesn't affect the overall connectivity.
The system just absorbs it.
It's so resilient, you'd have to remove almost every single node before the network actually fragments.
But the very thing that makes it so strong is also its greatest weakness.
It's the Achilles heel. Scale-free networks are hyper-fragile to targeted attack.
So if you know what you're doing.
If you have intelligence and you start removing the hubs first in order of their degree, the whole network just disintegrates.
You don't need to remove that many.
A tiny fraction. You take out the handful of most connected nodes and the entire system shatters into isolated pieces.
And this isn't a new idea. People were thinking about this vulnerability decades ago.
Oh yeah, go back to the Cold War.
Yeah.
In 1959, Paul Barron at RAND was trying to design a communication system that could survive a nuclear attack.
Yeah.
He specifically warned against centralized networks, the kind that look a lot like scale-free ones, because if you take out the center, the whole thing dies. The irony is the internet we ended up building has exactly that fragile structure.
And finally, this all brings us back to where we started. Cascading failures.
The domino effect.
Yeah.
A local failure overloads a neighbor, which then fails, which overloads its neighbors.
An avalanche.
And we see it in power blackouts, financial meltdowns, even in how information cascades across Twitter.
And what's really mind-bending is the universality of it all.
When scientists actually measure the size of these avalanches, blackout sizes, retweet storms, even the energy from earthquakes, they all follow the same power law distribution.
They have the same mathematical signature.
And the exponents, the numbers describing that curve, are strikingly similar. Between 1.6 and 2.0, it suggests that even though electricity and tectonic plates are completely different, the underlying network dynamics are driving the exact same universal pattern of collapse.
Wow. So this has been an amazing arc. We started with the very specific problem of finding one person in Iraq.
And ended up with these two universal laws of complexity. Small worlds and the scale-free property.
We saw how that architecture is built through growth and this rich get richer effect.
And how that same structure creates this paradox. It's super resilient to random error, but terrifyingly vulnerable to intelligent attack. It even dictates the pattern of how things fall apart on a global scale.
The big takeaway for me is that the wiring diagram is often more important than what's being wired. The rules of connection seem to naturally favor this concentration of everything. Influence, resources, you name it.
And it comes full circle. When you look at how we study these things, In science itself, the top 1% of papers now get a share of citations that looks a lot like the income share of the top 1% of the population.
And that's getting more extreme.
It is. Because as the amount of information explodes, we have to rely on crowdsourcing to find what's important. We follow the links. And that process, by its very nature, is preferential attachment. It always favors the hubs.
So if preferential attachment and fitness are what drive success in our world, in science, in tech, in wealth, we'll leave you with this final thought to chew on. We know individual talent is a part of fitness, but if success is so overwhelmingly driven by this ability to attract links, what fundamental mechanisms or societal structures, beyond mere individual talent, dictate who or what gains fitness in the first place?